Right now, as you watch this video, there's a war brewing inside your body. Your immune system, a microscopic army with the firepower to level entire cities, is making a decision that could change your life forever. In 2025, 50 million Americans are living with diagnosed autoimmune diseases, where the immune system attacks healthy tissue instead of protecting it. That's 8% of the population, and this number climbs by 3 to 12% annually across different conditions. Their body's defenders didn't just fail, they committed the ultimate act of treason. They turned their weapons on the very people they swore to protect. But how does a system designed for perfect protection become a weapon of mass destruction? The architecture of betrayal. The architecture of betrayal starts with a system so sophisticated, it makes the most advanced military defense network look like a child's toy. Your immune system operates the most complex security apparatus ever created, running continuous surveillance on every molecule that enters your body. This isn't just checking IDs at a checkpoint. It's analyzing the molecular fingerprints of millions of proteins every single second, each scan determining whether something lives or dies. Think of proteins as the ultimate identification cards. Each one carries a unique three-dimensional shape that serves as an unbreakable security code. Your body manufactures approximately 100,000 different distinct proteins, and your immune system has memorized every single one. These molecular signatures work like an incredibly advanced facial recognition system, where immune cells act as security guards, constantly scanning crowds for anyone who doesn't belong. The scale of this operation is staggering. Right now, millions of potent immune cells are patrolling your bloodstream, tissues, and organs, each one equipped with molecular scanners that can identify threats rapidly. They're checking protein shapes on the surface of every cell they encounter, comparing them against an internal database of authorized personnel. When they find a match, they move on. When they don't, they kill without hesitation. This system processes identity checks at a rate that would crash any computer network. Every heartbeat pushes these cellular security guards through new territories, where they encounter millions of proteins requiring verification. The immune cells don't just look at one protein at a time. They scan entire molecular neighborhoods, checking dozens of protein shapes simultaneously while moving through tissue at incredible speed. But here's where the architecture becomes terrifying. Your immune system doesn't just recognize foreign proteins, it has the firepower to eliminate entire cellular districts when it detects a threat. These aren't surgical strikes. When immune cells identify an enemy, they deploy chemical weapons that can destroy healthy tissue in the surrounding area. They call in reinforcements that flood the region with inflammatory molecules, turning peaceful cellular neighborhoods into war zones. The recognition system works through molecular signatures that function like highly sophisticated barcodes. Each protein displays specific amino acid sequences on its surface, creating patterns that immune cells read like a security scanner reads a badge. These patterns contain information about where the protein came from, what it does, and most importantly, whether it belongs in your body. Immune cells carry receptor molecules that work like molecular keys, each one designed to fit specific protein shapes. When a receptor encounters its matching protein, it triggers a cascade of signals that either grants clearance or initiates destruction. This lock-and-key system operates with precision that would make a Swiss watchmaker jealous, yet it's happening millions of times per second throughout your body. The stakes couldn't be higher. When this recognition system works correctly, it protects you from infections, cancers, and toxins that would otherwise kill you. But when it fails, it doesn't just make occasional mistakes. It launches coordinated military campaigns against your own healthy tissue. The same immune cells that normally protect your pancreas suddenly identify insulin-producing cells as foreign invaders. The defenders of your joints start attacking cartilage as if it were a bacterial infection. This isn't random violence. When immune cells turn against you, they bring the full force of their training and weaponry to bear on specific targets. They release cytotoxic chemicals that punch holes in cell membranes. They recruit other immune cells to join the attack. They establish persistent inflammatory responses that can last for decades, turning your own body into a battlefield where you're both the aggressor and the victim. The recognition system has built-in vulnerabilities that make betrayal almost inevitable. The protein shapes that immune cells learn to recognize aren't perfect templates. They're approximate patterns with room for interpretation. This flexibility is necessary because proteins can change shape slightly due to temperature, pH, or chemical modifications. But the same flexibility creates opportunities for catastrophic errors. Your immune system faces a similar challenge, but with molecular faces instead of human ones. A protein that's supposed to be recognized as self might undergo a minor shape change that makes it look foreign. Or a foreign protein might evolve to look almost identical to one of your own proteins, creating confusion that leads to friendly fire. The system must also distinguish between billions of different protein shapes while operating under intense time pressure. Immune cells can't spend minutes analyzing each protein they encounter. They have seconds to make life or death decisions. This speed requirement forces them to rely on pattern recognition shortcuts that occasionally produce false positives. There's another layer of complexity. Your immune system doesn't just recognize individual proteins. It reads combinations of proteins like sentences in a molecular language. A single cell might display dozens of different protein shapes on its surface, creating a complex signature that immune cells must interpret correctly. If even one protein in this signature looks suspicious, the entire cell becomes a target. The training process that's supposed to prevent this catastrophic failure operates under its own set of constraints. Immune cells must learn to recognize thousands of self-proteins while simultaneously remaining capable of detecting new threats. This creates an inherent tension between self-tolerance and protective immunity. Push too hard toward self-tolerance, and you become vulnerable to infections. Push too hard toward protection, and you risk autoimmune disease. The molecular recognition system also faces evolutionary pressure from pathogens that actively try to fool it. Bacteria and viruses have spent millions of years perfecting molecular disguises that allow them to slip past immune surveillance. Some of these disguises involve creating proteins that look almost identical to your own proteins, a strategy that can backfire spectacularly when your immune system learns to attack the disguise and ends up attacking you. Modern life has introduced new challenges that this ancient system wasn't designed to handle. Environmental toxins can modify protein shapes in ways that make them look foreign. New foods contain proteins that your immune system has never encountered. Stress hormones can alter how immune cells interpret molecular signatures. Even the bacteria living in your gut can influence how your immune system reads protein patterns. The architecture of betrayal isn't a design flaw, it's an inevitable consequence of building a system complex enough to protect you from the countless threats in a dangerous world. Every security system has vulnerabilities, and biological security systems are no exception. The question isn't whether your immune system will make mistakes, but when and how those mistakes will manifest. The recognition system that keeps you alive today carries within it the seeds of its own rebellion. But before these cellular traitors can wreak havoc, they must first survive the most brutal training program ever devised, the Academy of Elimination. Your body operates a training facility more ruthless than any military academy in history. This installation, called the Thymus, sits just above your heart and runs a highly stringent selection process that eliminates most newly formed T cells to prevent autoimmunity. New immune cells arrive here fresh from the bone marrow, eager to serve and protect. What they don't know is that over 90% of them will be systematically destroyed before they ever see active duty. The Thymus functions as a specialized elimination center where young T cells face a series of increasingly difficult tests. These aren't written exams or physical fitness challenges. These are life-or-death evaluations where failure means immediate execution. Every T cell that enters this facility must prove it won't attack your own body. If it shows even the slightest recognition of your proteins, it dies instantly. The selection process begins with basic training. Newly arrived T cells encounter proteins from your own tissues presented by instructor cells. This isn't a gentle introduction. The instructor cells display fragments of proteins from your heart, liver, kidneys, brain, and every other organ. They show the T cell samples of insulin, collagen, myelin, and thousands of other cell proteins. The T cells must demonstrate complete ignorance of these molecular signatures. Any T cell that reacts to these cell proteins receives an immediate death sentence. The instructor cells don't give warnings or second chances. They release chemical signals that would trigger the reactive T cell to self-destruct. The dying cell breaks apart, and specialized cleanup crews remove the debris. This process happens millions of times per day, creating a constant stream of cellular executions. The mathematics of this elimination process are staggering. Your thymus processes approximately 50 million new T cells daily. Of these, the vast majority are destroyed for showing recognition of self-proteins. Only a small fraction survive to enter circulation. This stringent failure rate might seem wasteful, but it's absolutely necessary. Any T cell that recognizes your own proteins as foreign represents a potential autoimmune time bomb. This double-edged selection process creates a fundamental tension. The training must be thorough enough to prevent autoimmunity, but not so harsh that it eliminates all defenders. If the thymus becomes too aggressive in its elimination, you end up with too few T cells to fight infections. If it becomes too lenient, you risk autoimmune disease. The thymus constantly adjusts its balance, but it's never perfect. Some T cells slip through this screening process despite carrying the potential for self-destruction. These escapees represent failures in the elimination system. They passed the basic test but harbored dangerous capabilities that weren't detected. Maybe they showed only weak recognition of self-proteins, just below the threshold for execution. Maybe they encountered proteins that weren't properly presented during their training. The thymus tries to compensate for these failures by creating regulatory T cells specifically designed to control other immune cells. These cellular police officers patrol your body looking for signs of autoimmune activity. They can shut down immune responses before they cause damage. But even these backup systems aren't foolproof. Regulatory T cells can be overwhelmed, corrupted, or simply outnumbered by aggressive immune cells. Peripheral tolerance mechanisms act as a secondary security system beyond the thymus. These mechanisms include energy, where potentially dangerous T cells become unresponsive to activation signals. They also include deletion, where self-reactive T cells are eliminated in the tissues rather than in the thymus. Regulatory T cells provide another layer of control, suppressing immune responses that target self-proteins. However, these backup systems sometimes fail. Environmental factors can override the safety mechanisms that keep self-reactive T cells dormant. Infections can create inflammatory conditions that activate previously quiet cells. Stress hormones can alter how immune cells interpret danger signals. Even changes in your gut bacteria can influence whether self-reactive T cells remain controlled or become activated. The terrifying mathematics reveal the true scope of this problem. Even with a 99.9% success rate in eliminating dangerous T cells, millions of potentially harmful cells escape into circulation. Your body contains approximately 1 trillion T cells at any given time. If just 0.1% of these cells have autoimmune potential, that's still 1 billion cellular time bombs circulating through your system. These escape cells don't immediately cause problems. They remain dormant, circulating through your bloodstream and tissues without causing obvious damage. They might patrol your body for years or decades without incident, but they're always there, waiting for the right combination of circumstances to activate them. They represent a constant threat that most people never realize they're carrying. The dormant cells maintain their dangerous potential through molecular memory. They carry surface receptors that can recognize cell proteins, but these receptors remain inactive under normal conditions. The cells need specific activation signals to become fully functional. These signals might come from infections, injuries, or other inflammatory events that create the right chemical environment. Environmental factors play a crucial role in determining whether these cellular time bombs ever explode. Viral infections can create inflammatory conditions that activate dormant self-reactive cells. Bacterial infections can present proteins that look similar to your own proteins, confusing the immune system. Physical trauma can release self-proteins in unusual contexts that trigger immune responses. The gut microbiome has emerged as a particularly important factor in autoimmune activation. The bacteria living in your intestines help train your immune system and maintain tolerance to self-proteins. Disruptions to this bacterial community can remove important regulatory signals, allowing self-reactive T cells to become activated. Antibiotic treatments, dietary changes, and infections can all alter the microbiome in ways that increase autoimmune risk. Modern life has introduced new environmental triggers that the thymus selection process never anticipated. Industrial chemicals can modify protein shapes in ways that make them look foreign. Food additives can create new molecular patterns that confuse immune cells. Air pollution can create inflammatory conditions that activate dormant self-reactive cells. The chilling reality is that everyone carries these cellular time bombs. Right now, you have millions of T cells circulating through your body with the potential to trigger autoimmune diseases. They pass through the thymus screening process, but they still carry dangerous capabilities. Whether they ever activate depends on a complex interplay of genetic factors, environmental triggers, and sheer luck. But the most dangerous activation doesn't come from internal failures alone. Masters of disguise, The most sophisticated threat comes from pathogens that have mastered molecular mimicry, creating proteins that serve as perfect forgeries of your own cellular identification cards. This infiltration technique represents the ultimate espionage operation, where foreign invaders wear stolen molecular uniforms to blend seamlessly into your body's landscape. Streptococcus bacteria demonstrate this deception with deadly precision. Their M protein shares a heptad repeat structure with cardiac myosin, the protein that powers your heart muscle contractions. This isn't coincidental similarity. It's evolutionary camouflage that allows the bacteria to hide from immune detection while simultaneously priming your immune system to attack your own heart valves. When your body fights the streptococcal infection, it creates antibodies that recognize both the bacterial protein and your cardiac tissue as identical threats. The structural similarity between these proteins reaches up to 80% in some cases, making them virtually indistinguishable to immune cells conducting routine security checks. Streptococcus proteins don't just look like human collagen, they function similarly enough to integrate into your tissue architecture. The bacteria essentially wear your collagen as a molecular mask, allowing them to hide in plain sight while your immune system patrols right past them. This camouflage strategy inhibits the normal process where immune cells engulf and destroy foreign invaders. Human cytomegalovirus takes this deception even further by mimicking MHC molecules, the very proteins your immune system uses to identify cells as belonging to you. The virus creates fake MHC proteins that display on infected cell surfaces, essentially forging the molecular passports that immune cells check to determine friend from foe. This allows infected cells to avoid detection and destruction, giving the virus time to replicate and spread. Epstein-Barr virus demonstrates this evolutionary sophistication by creating proteins that share striking similarities with myelin, the insulation around your nerve fibers. The virus doesn't just coincidentally happen to produce myelin-like proteins. It has evolved these proteins specifically to confuse your immune system. When immune cells encounter these viral proteins, they learn to recognize them as threats. But the molecular similarity means they also begin to recognize your actual myelin as a threat. This mimicry creates deadly confusion during immune responses. When your immune system encounters the viral proteins, it mounts a vigorous attack, producing antibodies and activating T cells specifically designed to target the viral invaders. But these same antibodies and T cells can't distinguish between the viral proteins and your own similar proteins. The immune response that was meant to protect you becomes a weapon turned against your own tissues. Cross-reactivity represents the molecular equivalent of friendly fire. Your immune cells, trained to recognize and destroy the viral proteins, encounter your own proteins that share similar molecular shapes. The immune cells can't tell the difference. They attack both the virus and your own tissues with equal ferocity. This cross-reactive response can continue long after the original infection has been cleared, creating persistent autoimmune inflammation. Campylobacter jejuni, a common cause of food poisoning, produces proteins that closely resemble gangliosides found in nerve tissue. When your immune system fights the bacterial infection, it creates antibodies that can also attack your peripheral nerves, potentially causing Guillain-Barré syndrome, a condition where your immune system destroys the myelin around nerve fibers. The molecular mimicry is so precise that the immune system cannot distinguish between the bacterial proteins and your own nerve components. The geographic distribution of molecular mimicry-triggered autoimmunity reveals fascinating patterns. Multiple sclerosis rates vary dramatically across different latitudes, with higher rates in regions where Epstein-Barr virus infections are more common. Rheumatoid arthritis shows similar geographic clustering, often correlating with the presence of specific bacterial strains that produce collagen mimicking. Proteins. Modern travel and globalization have created unprecedented opportunities for molecular mimicry confusion. Your immune system evolved to deal with pathogens from your local environment, developing tolerance patterns based on the specific molecular mimics present in your geographic region. When you travel to new areas or when global trade brings new pathogens to your region, your immune system encounters molecular mimics it has never seen before. These novel molecular mimics can trigger autoimmune responses because your immune system lacks the evolutionary adaptations that would normally prevent cross-reactivity. A pathogen that coexists peacefully with immune systems in its native region might trigger severe autoimmune responses in people whose immune systems haven't evolved alongside that specific molecular mimic. The speed of modern travel compounds this problem. Historical human migrations occurred over generations, allowing immune systems time to adapt to new molecular mimicry patterns. Today, you can be exposed to pathogens from anywhere in the world within hours, giving your immune system no time to develop appropriate tolerance mechanisms. Climate change has also altered molecular mimicry patterns by changing the geographic distribution of pathogens. Bacteria and viruses that were historically confined to specific regions are now spreading to new areas as temperatures and weather patterns shift. These migrating pathogens bring their molecular mimicry strategies to populations that have never encountered them before. Our connected world means we're encountering molecular mimics our immune systems have never seen before. The pathogens circulating globally today include molecular mimicry strategies that evolved in isolation from human populations, only to be suddenly introduced through modern transportation and trade networks. Your immune system faces an unprecedented challenge, distinguishing between your own proteins and foreign molecular mimics it has no evolutionary experience recognizing. But molecular mimicry alone isn't enough to trigger autoimmune disease. Even when your immune system encounters these deceptive proteins, something more must happen to transform this confusion into sustained autoimmune attack. The presence of molecular mimics creates the potential for autoimmune disease, but the actual development requires a more complex sequence of events. The perfect storm protocol. This convergence creates what researchers call the perfect storm protocol, a catastrophic alignment of genetic predisposition, environmental triggers, and immune system activation that transforms dormant autoimmune potential into active destruction. The mystery of timing haunts these diseases. Why does type 1 diabetes suddenly strike an 8-year-old who seemed perfectly healthy just months before? Why does multiple sclerosis emerge in a college student during finals week? Why does rheumatoid arthritis appear after a routine bout of food poisoning? These diseases don't strike randomly. They wait for specific moments when multiple factors align in a sequence that activates the cellular time bomb circulating through your system. Genetic predisposition sets the stage, but doesn't write the script. You might carry genes that make your immune system more likely to attack your pancreas, but these genes can remain silent for decades. They're like loaded weapons sitting in storage, dangerous but inactive. The genes determine your vulnerability, but they don't determine your fate. Millions of people carry autoimmune risk genes without ever developing disease. Women face disproportionate risk, with overall U.S. prevalence reaching 5.8% in women compared to 3.5% in men, reflecting complex interactions between genetics, hormones, and immune function. Environmental triggers represent the spark that ignites the genetic powder keg. These triggers include viral infections that create molecular mimicry, hormonal fluctuations that destabilize immune tolerance, and genetic variations that alter immune cell training. The trigger doesn't have to be dramatic. A simple respiratory infection can flood your system with cytokines that wake up dormant immune cells. A minor cut can release proteins from damaged tissue that confuse your immune system. Even emotional stress can alter hormone levels in ways that destabilize immune tolerance. The concept of the second hit reveals how seemingly minor events can flip the switch on dormant autoimmune potential. Your immune system might encounter a viral protein that looks similar to your own proteins. During the initial infection, your immune cells learn to recognize and attack this viral protein. But the molecular similarity means they also learn to recognize your own proteins as threats. This cross-training creates immune cells that will attack both the virus and your own tissues long after the original infection has cleared. Stress hormones create particularly dangerous conditions for immune system confusion. Cortisol, released during physical or emotional stress, suppresses certain immune functions while enhancing others. This hormonal disruption can override the normal tolerance mechanisms that prevent autoimmune responses. Chronic stress maintains elevated cortisol levels that gradually erode the barriers between immune activation and immune tolerance. Sleep deprivation compounds these effects by disrupting the circadian rhythms that regulate immune function. Your immune system follows a daily cycle of activity and rest. Sleep deprivation throws this cycle into chaos, creating periods when immune cells are hyperactive and more likely to attack healthy tissue. The combination of stress and sleep loss creates a biochemical environment where autoimmune activation becomes increasingly likely. The microbiome serves as either protector or accomplice in autoimmune development. The trillions of bacteria living in your gut help train your immune system to distinguish between threats and harmless substances. A healthy microbiome provides constant education that maintains immune balance, but antibiotic treatments, dietary changes, or infections can disrupt this bacterial community, removing crucial regulatory signals that prevent autoimmune responses. Dysbiosis, the imbalance of gut bacteria, can directly trigger autoimmune diseases. Certain bacterial strains produce molecules that mimic human proteins, creating the same molecular mimicry problems that occur with viral infections. Other bacteria produce toxins that damage the intestinal barrier, allowing foreign proteins to enter circulation and trigger immune responses. The loss of beneficial bacteria eliminates protective factors that normally suppress autoimmune activity. Epitope spreading represents one of the most insidious aspects of autoimmune perfect storms. Initially, your immune system might target a single protein in a specific tissue, but the inflammatory response causes collateral damage that exposes other proteins from the same tissue. These newly exposed proteins become additional targets for immune attack. The autoimmune response spreads like wildfire, recruiting more immune cells and targeting more tissue components. This spreading process can jump between different organs and tissues. An autoimmune attack that begins in joint tissue might eventually target proteins in the heart, kidneys, or nervous system. The immune cells trained to attack one type of protein encounter similar proteins in other tissues and expand their campaign of destruction. What begins as a localized problem becomes a systemic assault on multiple organ systems. The unpredictable nature of trigger events makes autoimmune diseases particularly cruel. Two people with identical genetic backgrounds might experience the same infection, but only one develops autoimmune disease. The difference might come down to timing, stress levels, sleep quality, or even random variations in how their immune systems respond to the trigger. This randomness means that autoimmune diseases can strike anyone, regardless of how carefully they manage their health. Some individuals experience multiple potential triggers without developing disease, while others succumb to the first significant challenge. The difference often lies in the precise alignment of factors. One person might encounter a trigger when their immune system is well regulated and their microbiome is healthy. Another might face the same trigger during a period of stress, sleep deprivation, and gut dysbiosis. The identical trigger produces completely different outcomes based on the internal conditions at the moment of exposure. The cascading effects of autoimmune activation can continue for months or years after the initial trigger event. Once the immune system learns to attack cell proteins, it doesn't easily forget this lesson. The inflammatory cascade creates tissue damage that exposes more cell proteins, feeding the autoimmune response. Stress from the disease itself can perpetuate the hormonal disruptions that maintain immune dysfunction. The sobering truth about autoimmune diseases is that they often result from a catastrophic alignment of factors that individually seem harmless. The genes you inherited, the infection you caught, the stress you experienced, and the sleep you lost all contribute to creating conditions where your immune system turns against you. Each factor appears manageable in isolation, but their convergence creates a perfect storm that can transform a healthy immune system into a weapon of self-destruction. Yet even as we understand these traditional patterns, our rapidly changing world is creating entirely new challenges that medical science is only beginning to recognize. The new faces of immune rebellion. Medical textbooks are being rewritten faster than ever before as entirely new autoimmune conditions emerge from the shadows. These aren't variations of known conditions or better classifications of existing problems. These are completely novel ways for your immune system to turn against you, created by the unprecedented environmental and technological changes of modern life. Environmental changes have fundamentally altered the molecular landscape your immune system must navigate. The air you breathe contains synthetic particles that didn't exist when your immune system evolved. The water you drink carries chemical residues from pharmaceutical manufacturing and industrial processes. The surfaces you touch are coated with antimicrobial agents that kill bacteria but leave behind molecular fragments your immune system has never encountered. Each of these exposures creates new protein targets that can trigger autoimmune responses in susceptible individuals. New technologies have introduced molecular patterns that your immune system interprets as threats. The electromagnetic fields from wireless devices alter protein structures in subtle ways that can trigger immune recognition. Blue light from screens affects melatonin production, which in turn influences immune cell behavior. The plastics in food packaging release compounds that bind to proteins and create hybrid molecules your immune system treats as foreign invaders. These technological exposures accumulate over time, creating a molecular burden that eventually overwhelms immune tolerance mechanisms. Modern lifestyles have accelerated the pace of immune system challenges beyond what natural selection prepared us for. Processed foods contain preservatives and additives that create inflammatory responses in people with specific genetic backgrounds. Sleep disruption from artificial lighting and constant connectivity throws immune circadian rhythms into chaos. Social media stress triggers cortisol release patterns that suppress regulatory immune cells. The combination of these lifestyle factors creates conditions where new autoimmune diseases can emerge and flourish. Digital device exposure has been linked to several emerging autoimmune conditions that affect connective tissues and nervous system function. Prolonged screen time creates repetitive strain patterns that damage proteins in ways that trigger immune responses. The heat generated by devices held close to the body alters local protein conformations, making them targets for autoimmune attack. Electromagnetic radiation from wireless connections appears to influence immune cell migration patterns, potentially directing autoimmune responses towards specific tissue types. New food additives represent another frontier for autoimmune disease development. Artificial sweeteners interact with gut bacteria in ways that produce inflammatory metabolites. Flavor enhancers create protein modifications that trigger immune responses in people with particular genetic variants. Preservatives accumulate in tissues over time, eventually reaching concentrations that activate immune surveillance mechanisms. The regulatory approval process for these additives tested them individually, but nobody predicted how they would interact with each other or with other environmental exposures. Environmental toxins have created entirely new categories of autoimmune targets. Microplastics in drinking water bind to proteins and create complex molecular structures that immune cells interpret as foreign. Industrial chemicals in household products modify protein surfaces in ways that trigger autoimmune recognition. Agricultural pesticides accumulate in fatty tissues and gradually release modified proteins that stimulate immune responses. The latency period for these toxin-induced autoimmune conditions can span decades, making them difficult to diagnose and treat. COVID-19 and other recent pandemics have triggered new forms of autoimmune responses that medical science is still struggling to understand. Long COVID includes autoimmune components where immune cells continue attacking tissues long after the virus has been cleared. The spike protein from SARS-CoV-2 shares molecular similarities with proteins in blood vessels, heart tissue, and nervous system structures. This molecular mimicry has created autoimmune conditions affecting multiple organ systems simultaneously, producing symptom patterns that don't fit traditional disease classifications. Post-viral autoimmune syndromes have emerged as a distinct category of disease following recent pandemic infections. These conditions combine features of chronic fatigue syndrome, autoimmune neuroinflammation, and vascular dysfunction. The immune system appears to remain in a hyperactive state months or years after viral clearance, attacking tissues that were damaged during the acute infection. This persistent immune activation creates progressive tissue damage that worsens over time without appropriate intervention. Neoantigens represent the newest frontier in autoimmune disease development. These are protein targets created by modern life that didn't exist in nature until recently. Chemical modifications from pollution create altered proteins that immune systems recognize as foreign. Food processing generates protein fragments that trigger immune responses in genetically susceptible individuals. Even medical treatments can create neoantigens through drug interactions that modify normal protein structures. The populations most at risk for these emerging conditions include young adults who have lived their entire lives in highly technological environments. Children born after 2000 have been exposed to unprecedented levels of electromagnetic radiation, synthetic chemicals, and processed foods. Their immune systems developed in this altered environment, making them more susceptible to autoimmune responses against modern molecular targets. Urban populations face higher exposure levels to many of these triggers, creating geographic clustering of emerging autoimmune conditions. Diagnostic challenges posed by these emerging conditions are overwhelming traditional medical approaches. Symptoms don't fit established patterns, making diagnosis difficult and delayed. Standard autoimmune testing panels don't include antibodies against the novel targets involved in these conditions. Patients often see multiple specialists before receiving appropriate diagnosis and treatment. The lack of established diagnostic criteria means many cases go unrecognized for months or years. The clinical presentation of emerging autoimmune conditions often combines features from multiple traditional disease categories. Patients might experience neurological symptoms, skin manifestations, joint pain, and digestive problems simultaneously. This multi-system involvement reflects the widespread distribution of the molecular targets involved in these new conditions. Traditional medical specialization struggles to address diseases that affect multiple organ systems through novel mechanisms. Our rapidly changing world is creating new ways for immune systems to turn against us at an unprecedented pace. The molecular targets, environmental triggers, and population vulnerabilities involved in these emerging conditions reflect the profound impact of modern life on human immune function. But these new autoimmune threats don't affect everyone equally. The distribution of autoimmune diseases reveals striking patterns that expose deeper truths about vulnerability in modern society. The demographics of betrayal. Women bear the heaviest burden of autoimmune betrayal, accounting for 63% of all diagnosed cases compared to 37% for men. This 1.7 to 1 female-to-male ratio persists across virtually every autoimmune condition, from lupus to multiple sclerosis to rheumatoid arthritis. The disparity isn't subtle. It represents a fundamental biological reality affecting millions of lives. Recent research tracking over 15 million Americans found that 4.6% of the U.S. population has been diagnosed with at least one autoimmune disease, with women facing disproportionate risk across all age groups. The X chromosome appears to hold crucial keys to understanding this female vulnerability. Women possess 2 X chromosomes, while men have 1 X and 1 Y chromosome. This chromosomal difference creates unique genetic conditions that influence immune system behavior. Genes on the X chromosome play significant roles in immune function, and having 2 copies of these genes may create situations where immune responses become hyperactive or misdirected. The process of XN activation, where 1 X chromosome is randomly silenced in each cell, can create cellular mosaicism that confuses immune recognition systems. Hormonal fluctuations throughout women's lives create additional layers of autoimmune risk. Estrogen levels influence immune cell activity in complex ways, sometimes enhancing immune responses and sometimes suppressing them. Pregnancy creates dramatic hormonal shifts that can trigger autoimmune diseases in susceptible women. Many autoimmune conditions flare during pregnancy or appear for the first time in the postpartum period. Menopause brings another set of hormonal changes that can destabilize immune tolerance mechanisms that previously kept autoimmune potential in check. Age patterns reveal disturbing trends that challenge traditional medical assumptions. Autoimmune conditions increasingly affect younger populations, with diagnoses occurring in children and teenagers at unprecedented rates. Type 1 diabetes now strikes children as young as toddlers. Multiple sclerosis, once considered a disease of young adults, now affects teenagers with increasing frequency. Inflammatory bowel diseases appear in elementary school children who should be years away from such serious health challenges. This shift toward younger onset reflects fundamental changes in environmental exposures and lifestyle factors. Children today encounter chemical exposures, processed foods, and electromagnetic radiation that previous generations never experienced. Their immune systems develop in environments saturated with synthetic materials and artificial stimuli. The combination of genetic predisposition and novel environmental triggers creates conditions where autoimmune diseases can emerge much earlier in life than evolutionary history would predict. Geographic patterns create fascinating maps of vulnerability and protection. Multiple sclerosis rates increase dramatically with distance from the equator, creating clear latitude-dependent patterns. Northern regions of the United States and Europe show significantly higher rates than southern areas. This geographic distribution suggests that sunlight exposure, vitamin D levels, and seasonal variations in immune function play crucial roles in autoimmune disease development. Certain regions show clustering patterns that can't be explained by genetics alone. The Great Lakes region has unusually high rates of multiple autoimmune conditions. Industrial areas with heavy chemical pollution show elevated autoimmune disease rates. Agricultural regions with intensive pesticide use demonstrate specific autoimmune patterns. The concept of autoimmune clusters extends beyond individual diagnoses to encompass complex medical situations where multiple immune system failures occur simultaneously. Research reveals that 34% of individuals diagnosed with one autoimmune disease develop additional autoimmune conditions, creating cascading patterns of immune dysfunction. These clusters suggest shared genetic vulnerabilities and environmental exposures that create conditions where autoimmune diseases can proliferate within specific populations. Family clustering patterns reveal how genetic predisposition interacts with shared environmental exposures. Multiple family members might develop different autoimmune diseases, suggesting common underlying immune system vulnerabilities that manifest in various ways. These family patterns provide crucial insights into genetic risk factors and help identify individuals who need careful monitoring for early signs of autoimmune disease development. Modern lifestyle factors are fundamentally reshaping traditional autoimmune demographics. Sleep deprivation, chronic stress, processed food consumption, and sedentary behavior create conditions that promote autoimmune disease development across all demographic groups. Social media stress and digital device exposure affect immune function in ways that previous generations never experienced. The pace of modern life creates chronic low-level inflammation that gradually erodes immune tolerance mechanisms. Urban living patterns expose populations to air pollution, electromagnetic radiation, and chemical exposures that alter immune system function. Rural populations face different challenges, including pesticide exposure, well water contamination, and limited healthcare access. These environmental differences create distinct autoimmune disease patterns that vary between urban and rural populations. Global autoimmune disease incidence has risen by 19.1% across different conditions, reflecting the profound impact of modern environmental changes on immune system function. This dramatic increase spans all demographic groups but affects certain populations more severely than others. The demographic patterns reveal that autoimmune diseases serve as a mirror, reflecting the stresses and vulnerabilities of different populations in modern society. Understanding these demographic patterns provides crucial insights for early detection strategies, particularly in high-risk groups where intervention could prevent or delay disease onset. Women of childbearing age, individuals with family histories of autoimmune disease, and populations in geographic hotspots represent priority targets for monitoring and preventive interventions. The demographic data also guides the development of targeted therapies that address the specific vulnerabilities of different population groups. These patterns of vulnerability create a roadmap for understanding not just who develops autoimmune diseases, but how the immune system selects its targets once betrayal begins. The demographic data reveals the populations at risk, but the true horror lies in understanding how precisely these rogue immune cells execute their campaigns of destruction. Weapons of precision destruction. When immune cells turn rogue, they don't attack randomly like a drunk soldier firing into a crowd. They target with surgical precision, each autoimmune disease representing a specialized warfare unit with preferred targets and attack strategies. Multiple sclerosis sends immune cells specifically after myelin, the insulation around nerve fibers. Rheumatoid arthritis deploys cellular armies that focus exclusively on joint tissue. Type 1 diabetes launches precision strikes against insulin-producing cells in the pancreas. This isn't collateral damage. This is coordinated, targeted destruction carried out by your own cellular military. The mechanisms behind this targeted destruction reveal how autoimmune cells navigate to specific organs and tissues with extraordinary accuracy. These cells don't wander aimlessly through your bloodstream hoping to stumble across their targets. They follow molecular GPS systems that guide them directly to the tissues they're programmed to destroy. The precision rivals that of guided missiles, with immune cells traveling through miles of blood vessels to reach specific target locations. Chemokines serve as the molecular GPS systems that guide immune cells to their targets. These protein signals create chemical gradients that immune cells follow like bloodhounds tracking a scent. Different tissues release different chemokines, creating unique chemical signatures that attract specific types of immune cells. CXCL13, for example, specifically guides immune cells to lymph nodes, creating targeted pathways for cellular migration. When autoimmune cells detect these chemical signals, they migrate toward the source with single-minded determination. The chemokine gradients essentially create highways that direct immune cells to their intended targets. The chemokine system operates with terrifying efficiency. Immune cells express specific receptor molecules that bind to particular chemokines, creating lock and key relationships that determine which cells respond to which signals. A T cell programmed to attack myelin will express receptors for chemokines released by nervous tissue. A B cell targeting joint proteins will respond to chemokines produced by synovial tissue. This molecular specificity ensures that autoimmune attacks reach their intended targets rather than causing random destruction. Research published in February 2025 in Nature revealed that granzyme K produced by CD8 plus T cells drives complement activation against cell tissues, offering a new therapeutic target. This protein drives tissue damage and inflammation by activating the complement system against the body's own tissues. The discovery of granzyme K demonstrates how autoimmune cells deploy specialized molecular weapons designed for maximum tissue destruction. Certain tissues enjoy immune privilege status, protected areas where immune cells normally cannot enter or function. The brain, eyes, and reproductive organs exist behind specialized barriers that prevent immune cell infiltration. These barriers develop evolutionarily to protect critical organs from immune system damage. However, some autoimmune diseases breach these protected areas with devastating consequences. Multiple sclerosis breaks through the blood-brain barrier, allowing immune cells to attack nervous tissue that should be completely off-limits. The breach of immune privilege sites represents one of the most serious forms of autoimmune disease. When immune cells penetrate the blood-brain barrier, they encounter tissue that has never been exposed to immune surveillance. The brain contains proteins that immune cells have never learned to recognize as self because they were hidden behind protective barriers. This lack of familiarity can trigger aggressive immune responses against brain tissue, leading to rapid and severe neurological damage. Why certain tissues are more vulnerable to autoimmune attack than others relates to their molecular composition and accessibility. Tissues with high protein turnover rates present more opportunities for immune recognition errors. Organs with extensive blood vessel networks provide easier access routes for infiltrating immune cells. Tissues that undergo frequent cellular replacement create more chances for immune cells to encounter self-proteins in inflammatory contexts that promote autoimmune responses. The cascading effects of autoimmune destruction create expanding zones of tissue damage that trigger attacks in previously healthy areas. When immune cells destroy tissue in one location, they release cellular debris that contains proteins from damaged cells. These released proteins can travel to other areas of the body where they trigger additional autoimmune responses. The process, called epitope spreading, allows autoimmune diseases to progressively involve more tissues and organs over time.
Epitope spreading transforms localized autoimmune attacks into systemic diseases that affect
multiple organ systems. An autoimmune response that begins in joint tissue might spread to attack proteins in the heart, kidneys, or nervous system. The immune cells trained to attack joint proteins encounter similar proteins in other tissues and expand their campaign of destruction. This spreading process explains why many autoimmune diseases become more severe and involve more organ systems as they progress. The discovery of CRITch1, a protein that regulates T-cell activation, offers new insights into how autoimmune targeting can be controlled. Research shows that CRITch1 acts as a partial brake that regulates T-cell response, indicating that drugs could be designed to control the protein's activity. In autoimmune diseases, CRITch1 could slow down the activation of T-cells, offering a way to fine-tune immune responses and reduce tissue-specific destruction. Revolutionary therapeutic approaches are emerging that can intercept and reprogram these cellular weapons. CAR T-cell therapy, originally developed for cancer treatment, is being adapted to target immune cells that contribute to chronic inflammation and autoimmunity. CD19-directed CAR T therapy targets B cells that contribute to chronic inflammation and autoimmunity. Schett's 2022 investigator-led trial demonstrated remarkable success, with 5 systemic lupus erythematosus patients achieving sustained remission after treatment. Approximately 95 trials of autologous cell therapies are currently investigating these approaches across different autoimmune conditions. These therapies may redefine long-term disease control by resetting immune tolerance and eliminating the cellular weapons responsible for tissue destruction. The approach involves genetically engineering T cells to recognize and eliminate the specific immune cells causing autoimmune damage. Regulatory T cell therapies represent another promising avenue for controlling autoimmune targeting. These specialized immune cells normally suppress excessive immune responses and maintain tolerance to self-proteins. Researchers are developing methods to expand and enhance regulatory T cells, creating cellular peacekeepers that can halt autoimmune attacks before they cause irreversible tissue damage. The chilling realization that emerges from understanding autoimmune targeting mechanisms is that these diseases represent the ultimate precision warfare, with your own cells serving as both weapons and targets. The immune system's capacity for targeted destruction, normally used to eliminate threats, becomes a weapon of mass destruction when directed against healthy tissue. Your cellular military doesn't just turn against you. It does so with the same precision and efficiency that normally keeps you alive. But understanding these targeting mechanisms is opening unprecedented opportunities to intervene before the destruction begins. The molecular pathways that guide immune cells to their targets are becoming roadmaps for therapeutic intervention. The chemical signals that coordinate autoimmune attacks are being decoded and disrupted. The precision that makes autoimmune diseases so devastating is also creating precise opportunities for medical intervention that could transform how we approach these conditions entirely. The surveillance revolution. The breakthrough of 2025 has fundamentally transformed our relationship with autoimmune diseases. For the first time in medical history, we can detect immune system rebellion before it causes irreversible damage. This isn't about better symptom recognition or faster diagnosis after disease onset. This is about identifying autoimmune processes years before symptoms appear, during the silent period when your immune system is planning its attack but hasn't yet pulled the trigger. New biomarker technologies represent the vanguard of this diagnostic revolution. These sophisticated tools can identify autoimmune processes long before clinical symptoms manifest, providing unprecedented opportunities for early intervention. The technologies include AI-powered immune profiling, advanced autoantibody panels, and genetic risk scoring, creating a comprehensive assessment framework that evaluates individual predisposition to autoimmune conditions. This technological leap represents more than incremental improvement. It's a fundamental shift toward predictive rather than reactive medicine. The concept of pre-autoimmunity has emerged as a crucial window of opportunity. This phase represents the period when immune system dysregulation is brewing beneath the surface, characterized by subtle immunological changes that can be detected through advanced biomarker technologies. During pre-autoimmunity, your immune system shows signs of instability and potential rebellion, but hasn't yet launched full-scale attacks against your tissues. This state can persist for months or years, creating a critical intervention window that previous generations of medicine never knew existed. Pre-autoimmunity. Detection involves monitoring specific immune cell populations that show signs of activation or abnormal behavior. Researchers can now identify T cells that display markers indicating they're preparing to attack self-tissues. B cells that begin producing autoantibodies in small quantities can be detected long before these antibodies reach disease-causing levels. Cytokine patterns in blood samples reveal inflammatory processes that precede tissue damage by substantial time periods. AI-powered immune profiling analyzes vast amounts of immunological data to identify patterns and predict autoimmune disease likelihood. Machine learning algorithms process complex datasets including genetic information, environmental factors, and lifestyle data to provide personalized risk assessments. These systems can detect subtle patterns in immune cell behavior that human analysis would miss, identifying combinations of risk factors that predict autoimmune disease development with remarkable accuracy. The AI systems continuously learn from new patient data, refining their predictive capabilities as they encounter more cases. They can identify immune signatures that correlate with specific autoimmune diseases, allowing for targeted monitoring and intervention strategies. Some AI platforms can predict which individuals will develop multiple sclerosis, rheumatoid arthritis, or type 1 diabetes years before traditional diagnostic methods would detect these conditions. Advanced autoantibody panels serve as another critical detection tool. These panels identify autoantibodies that mistakenly target the body's own tissues, often appearing years before clinical symptoms develop. The panels have become increasingly sophisticated, detecting broader ranges of autoantibodies with improved diagnostic accuracy. Modern panels can identify autoantibodies against hundreds of different cell proteins, creating detailed profiles of immune system targeting patterns. Genetic risk scoring integrates individual genetic makeup analysis to identify predispositions to autoimmune diseases. This information combines with environmental exposures and lifestyle choices to create comprehensive risk assessments. The scoring systems analyze complex genetic interactions that influence autoimmune susceptibility, revealing how evolution has shaped our immune vulnerabilities. Variants protective against Crohn's disease were linked to higher survival during the Black Death, demonstrating how historical selection favored aggressive immune genes that now contribute to autoimmune risk. Wearable devices and continuous monitoring are transforming autoimmune disease detection by providing real-time health insights. These devices track physiological parameters like heart rate variability, sleep patterns, and activity levels that can indicate early autoimmune activity. Continuous monitoring detects subtle changes that might otherwise go unnoticed, enabling timely intervention before disease progression occurs. Some wearable devices can detect inflammatory markers through skin sensors or analyze sweat composition for immune system indicators. Smart contact lenses can monitor tear film composition for autoimmune-related changes. Implantable sensors can provide continuous monitoring of immune cell activity in specific tissues. These technologies create comprehensive surveillance networks that alert both patients and healthcare providers to early signs of autoimmune activation. Personalized autoimmune risk assessment integrates genetic, environmental, and lifestyle factors to create tailored risk profiles. This approach enables precise assessment of individual autoimmune disease risk, facilitating personalized prevention and treatment strategies. The personalization represents a significant shift toward proactive healthcare, moving away from one-size-fits-all approaches toward individualized medicine. Risk assessment platforms consider factors like family history, geographic location, occupational exposures, dietary patterns, stress levels, and sleep quality. They analyze how these factors interact with genetic predisposition to create dynamic risk profiles that change over time. Individuals can modify their risk profiles through lifestyle interventions, environmental changes, or medical treatments. Early detection enables preventive interventions that were previously impossible. By identifying autoimmune processes early, healthcare providers can implement lifestyle modifications, targeted therapies, and other interventions to prevent or delay disease onset. This shift toward preventive healthcare represents a significant advancement in autoimmune disease management, offering potential to improve patient outcomes and reduce disease burden. The modern prevalence of autoimmune diseases in industrialized nations affects 7 to 10% of the population, reflecting how our evolved immune systems struggle with contemporary environments that lack the pathogen exposure that historically trained. Immune tolerance. Our aggressive immune responses, once essential for survival, now turn against us in sanitized modern environments. The ethical implications of predicting autoimmune diseases before they occur create complex considerations. Insurance companies might discriminate against individuals with high genetic risk scores. Employment opportunities could be affected by autoimmune disease predictions. Psychological impacts of knowing about future disease risk require careful consideration and support systems. However, the potential benefits of early detection and prevention may outweigh these concerns. Individuals with advanced warning can make informed decisions about their health, careers, and family planning. Healthcare systems can allocate resources more efficiently by focusing on high-risk individuals. Society can benefit from reduced healthcare costs and improved quality of life for people who avoid or delay autoimmune disease development. The hopeful revelation emerging from this surveillance revolution is that we're entering an era where autoimmune diseases might be detected and stopped before they cause any damage. The combination of advanced biomarker technologies, artificial intelligence, continuous monitoring, and personalized risk assessment creates unprecedented opportunities for autoimmune disease prevention. This represents a fundamental shift from treating autoimmune diseases after they develop to preventing them from developing in the first place. But detecting these diseases early is only the beginning of what's now possible. Precision counterattacks. The therapeutic revolution of 2025 has fundamentally transformed how we fight autoimmune diseases. Gone are the days of crude immune suppression that turned your entire defense system into a useless shell. Today's treatments operate with surgical precision, targeting only the problematic immune cells while leaving your protective immunity intact. This represents a complete shift from the sledgehammer approach of traditional immunosuppression to the scalpel-like precision of modern immune editing. Immune editing selectively removes only the rogue immune cells that cause autoimmune damage. Instead of shutting down your entire immune system, these treatments identify and eliminate specific cell populations that attack your own tissues. The process works like a highly trained sniper unit that can pick off enemy soldiers while leaving friendly forces completely unharmed. Your immune system maintains its ability to fight infections, recognize cancer cells, and perform all its protective functions while the autoimmune troublemakers are systematically eliminated. CAR T-cell therapy has emerged as one of the most promising breakthrough treatments for autoimmune diseases. This technology, originally developed to fight cancer, reprograms your own T cells to become precision weapons against autoimmune cells. The process involves extracting T cells from your blood, genetically modifying them to recognize and destroy specific autoimmune cell types, then reinfusing them back into your body. These modified cells act like guided missiles, seeking out and destroying the immune cells that cause autoimmune damage. The results from CAR-T therapy have been remarkable. Some patients with systemic lupus erythematosus, myositis, and systemic sclerosis have experienced drug-free remission after a single dose. This isn't temporary symptom relief. This is complete disease control that persists for months or years without additional treatment. The therapy essentially resets the immune system by eliminating the specific cell populations responsible for autoimmune attacks. Currently, approximately 85 different CAR-T therapeutic candidates are in clinical development across more than 380 clinical trials. Researchers are exploring various targets including CD19, CD20, CD22, CD38, and BCMA to selectively deplete specific B-cell subsets. These targets represent different molecular signatures on autoimmune cells, allowing for precise elimination of disease causing immune cells while preserving healthy immune function. Targeted B-cell depletion has become a cornerstone of precision autoimmune therapy. B cells play multiple roles in autoimmune disorders, including antibody production, antigen presentation, and cytokine release. By targeting specific B-cell populations, treatments can eliminate the cells that produce autoantibodies while preserving B cells that protect against infections. This selective approach prevents the immunodeficiency that plagued earlier treatments. Regulatory T-cell enhancement represents another frontier in precision autoimmune therapy. These cellular peacekeepers normally prevent autoimmune responses by suppressing overactive immune cells. In autoimmune diseases, regulatory T cells are often overwhelmed or dysfunctional. New treatments boost regulatory T cell numbers and function, restoring the natural balance that prevents immune system rebellion. Some therapies extract regulatory T cells from patients, expand them in laboratory conditions, then reinfuse them to restore immune tolerance. Personalized medicine is tailoring treatments to individual immune profiles and genetic backgrounds. Each person's autoimmune disease has unique characteristics based on their genetic makeup, environmental exposures, and specific immune system patterns. Modern treatments analyze these individual factors to create customized therapy plans. Genetic testing identifies which molecular pathways are most active in each patient's disease, allowing doctors to select treatments that target those specific mechanisms. The microbiome has become a powerful ally in new therapeutic approaches. Beneficial bacteria are being weaponized against autoimmunity through targeted probiotic treatments and microbiome modification. The gut-lung axis represents a particularly important therapeutic target where gut bacteria influence immune responses in the lungs and throughout the body. Specific bacterial strains produce short-chain fatty acids that regulate immune cell behavior and maintain tolerance to cell proteins. Gene editing techniques are targeting the human leukocyte antigen gene, which plays a key role in triggering autoimmune diseases. Researchers are modifying cells extracted from patients' bone marrow to treat the root causes of rheumatoid arthritis and other autoimmune diseases. This approach involves editing the HLA gene to potentially reset the immune system and restore normal function. Researchers have identified granzyme K as a potential therapeutic target. This protein drives inflammation and tissue damage by activating the complement system against the body's own tissues. Targeting granzyme K offers a more precise approach to selectively dampen harmful inflammation while preserving essential antimicrobial functions. The findings may inform new targeted treatments that block harmful immune activation and prevent tissue damage. A new syndrome called local immune effector cell-associated toxicity syndrome has been identified in patients treated with CD19 targeting CAR-T cell therapy. Unlike cytokine release syndrome, this toxicity is limited to organs affected by autoimmune conditions, is associated with B-cell depletion, and generally resolves on its own or with short-term steroid treatment. Understanding this syndrome allows for more precise management of treatment side effects. The potential for immune system reboots represents the ultimate goal of modern autoimmune therapy. These treatments could completely reset autoimmune processes, eliminating the immune memory that drives continued tissue attack. The approach would essentially give patients a fresh start with properly functioning immune systems that maintain tolerance to cell proteins. These precision counterattacks offer hope for the 15 million Americans living with autoimmune diseases, representing 4.6% of the population. New therapies offer hope, but require personalized assessment and long-term monitoring as over 100 autoimmune diseases persist. The combination of immune editing, personalized medicine, and regenerative approaches has the potential to transform disease management, moving from symptom control toward actual disease resolution. For those at risk or already affected, early screening under new guidelines could identify autoimmune processes before irreversible damage occurs. The window of opportunity for intervention has never been wider, but it requires proactive engagement with healthcare providers who understand these emerging diagnostic and therapeutic capabilities. Yet as we celebrate these medical advances, a deeper question emerges that challenges our understanding of why these diseases exist at all. If autoimmune conditions cause such suffering and disability, why haven't millions of years of evolution eliminated the genes that make them possible? The evolutionary paradox. The genetic architecture that creates autoimmune vulnerability reveals one of evolution's most profound contradictions. Frederick Peel, a professor of neurology at Karolinska Institute, explains that the genes promoting a highly reactive immune system, which can lead to autoimmune diseases, were advantageous in the past. These genetic variants helped humans survive infectious diseases, which were the primary cause of death throughout most of human history. Your ancestors needed aggressive immune systems to survive plagues, bacterial infections, and parasitic diseases that killed the majority of people before they could reproduce. The concept of evolutionary trade-offs reveals how genes that cause autoimmunity today provided crucial survival advantages in the past. An immune system that attacks your own tissues represents a catastrophic malfunction in the modern world. But in a world dominated by deadly infections, that same aggressive immune system meant the difference between life and death. Your genetic makeup reflects the survival pressures faced by thousands of generations of ancestors who lived in environments where infectious diseases posed constant threats. The Black Death pandemic provides compelling evidence of how autoimmune-associated genes provided protection against historical infectious diseases. Analysis of DNA samples from London cemeteries revealed that individuals with gene variants that increased the risk for Crohn's disease died at much lower rates during the pandemic. The genes that make immune systems more aggressive provided crucial protection against the bacterial infection that killed approximately half of Europe's population. This historical evidence demonstrates that autoimmune susceptibility genes weren't evolutionary mistakes. They were survival advantages that helped our ancestors survive pandemics that would have otherwise eliminated entire populations. The same genetic variants that predispose modern humans to autoimmune diseases allowed previous generations to survive infectious diseases that killed individuals with less aggressive immune systems. The hygiene hypothesis illuminates how our clean modern environment contributes to autoimmune disease increases. This theory suggests that reduced exposure to infections and microbes during early childhood leaves immune systems without proper training. The modern environment, characterized by improved hygiene, antibiotics, and vaccines, has dramatically reduced exposure to infectious diseases. This has created immune systems that are more aggressive for no good reason, making them vulnerable to autoimmune diseases. Children today grow up in sanitized environments that previous generations never experienced. They encounter fewer bacteria, viruses, and parasites during critical developmental periods when their immune systems are learning to distinguish between threats and harmless substances. This lack of microbial exposure leaves immune systems undertrained and prone to overreaction. The very cleanliness that protects us from infectious diseases may be creating conditions that promote autoimmune disease development. Rapid environmental changes have outpaced evolutionary adaptation, leaving us with mismatched immune systems. Human environments have transformed more rapidly in the past century than in the previous 1,000 years. We've eliminated most infectious diseases, introduced countless synthetic chemicals, altered our diets dramatically, and created living conditions that bear no resemblance to the environments where our immune systems evolved. The concept of evolutionary mismatch explains how modern triggers inappropriately activate ancient immune responses. Our immune systems evolved to function in environments filled with infectious threats, limited food diversity, and constant exposure to microorganisms. These systems now operate in sterile environments with processed foods, synthetic chemicals, and minimal microbial exposure. The mismatch between evolutionary programming and modern reality creates conditions where immune systems attack our own tissues. Modern triggers activate immune responses that were designed for completely different threats. Industrial chemicals trigger inflammatory responses intended for bacterial toxins. Processed foods activate immune pathways designed to handle parasitic infections. Stress hormones from modern life stimulate immune responses that evolved to handle acute physical threats. These mismatched responses create autoimmune diseases that our ancestors never experienced. The study of molecular mimicry, where pathogens evolved to mimic human proteins, provides insights into how evolutionary pressures shape both immune systems and the diseases that attack them. Pathogens that successfully mimic human proteins could evade immune detection, creating selective pressure for more aggressive immune responses. This evolutionary arms race produced immune systems capable of detecting subtle molecular differences, but also prone to attacking similar molecules in our own tissues. Research into granzyme K, a protein that drives tissue damage and inflammation by activating the complement system against the body's own tissues, demonstrates how evolutionary mechanisms continue to influence autoimmune disease development. This protein represents an ancient immune mechanism that served protective functions in our evolutionary past but now contributes to autoimmune tissue destruction. The question of whether autoimmune diseases represent the price we pay for surviving past pandemics reveals uncomfortable truths about human evolution. The genetic variants that protected our ancestors from infectious diseases now cause immune systems to attack healthy tissue. We carry the genetic legacy of survival strategies that are no longer needed but continue to influence our health in devastating ways. Understanding evolutionary origins is informing new therapeutic approaches that target the root causes of autoimmune diseases. Researchers are developing treatments that modulate the evolutionary pathways that lead to autoimmune responses. Some therapies focus on restoring the microbial exposures that immune systems evolved to expect. Others target the specific genetic variants that create autoimmune susceptibility. The profound insight that emerges from understanding autoimmune diseases through an evolutionary lens is that these conditions represent the echoes of our ancestors' survival strategies, now turned against us in a world they never imagined. The genes that allowed humans to survive plagues, infections, and parasitic diseases now create immune systems that attack our own tissues and environments that lack the threats they evolved to combat. We are living with the consequences of evolutionary adaptations that served our species well for millennia, but have become liabilities in a modern world. This evolutionary perspective transforms how we understand our relationship with these diseases and points toward a future where this ancient biological inheritance might finally be reconciled with the realities of modern life. The medical landscape of 2025 reveals autoimmune diseases as both humanity's greatest immunological challenge and our most promising frontier for precision medicine. These conditions affect approximately 15 million Americans, representing 4.6% of the population, with prevalence rising 3 to 12% annually across different conditions. Yet breakthrough treatments like CAR T-cell therapy are inducing drug-free remission in patients with lupus, myositis, and systemic sclerosis, fundamentally changing what's possible in autoimmune care. Understanding autoimmunity has reshaped our relationship with our own biology, revealing how evolutionary survival strategies that protected our ancestors now turn against us in sanitized modern environments. The future holds unprecedented hope through precision therapies that reprogram immune systems rather than suppress them, offering the possibility of actual disease resolution rather than lifelong management. Early detection through advanced biomarkers and personalized interventions represent the next frontier in preventing autoimmune diseases before they cause irreversible damage.